Hello, class. This is Doug again. The last section of the course right now, so let's get to it. This is going to be exponential and log equations. Let's start out with something easy. 2 to the x equals 16. You can tell by inspection x is going to equal 4. Or you can get fancy and go 2 to the x equals and rewrite 16 with a base that's same as that base. And 16 indeed is 2 to the fourth power, since 2 times 2 times 2 times 2 equals 16. And then when the bases are the same and they're equal to each other, that means the exponents have to be the same. So just set the exponents equal to each other and you're done. X equals 4. Or you can just tell by inspection, like I said. Okay, so what about if you have this one though? 17 is not a power of 2. So now it's a little harder. So we're going to need logarithms. Logarithms unlock the variable in the exponent. Logarithms unlock the exponents. So by definition, we can just say x equals log base 2 of 17 because that's the base is 2 in my exponential form. That's the base in the log form. And then you see the number 17, that's going to become the argument. And on the calculator, there is no base 2. So let's use the change of base formula. And all that means is do a good base, which is on the calculator, either base E or base 10. And in the numerator, you make the argument the same as the original. But in the denominator, you write down ln again and make the argument whatever that base is. So that, and that's the same thing as that, believe it or not. If you type both of these in your calculator, you'll get the same answer. Okay, let's move along to the next problem. How about if you have this exponential equation? It's good to identify what you're looking at. I see an equal sign, so it's an equation, and I see the variable in the exponent, so it's an exponential equation. Okay, to solve for x here, it's tempting to multiply the 10 times the 5, but you cannot do that. You got to follow order of operations, and this 5 is being raised to the x power. So exponents comes before multiplication, so you can't multiply the 10 by that base of 5. How about divide both sides by 10? Let's isolate that x factor by itself. Okay, so when we do that, we get that. Again, we just divided both sides by 10, and we get that. And then by inspection, you can tell x equals 2, because 25 is a power of 5. So you don't need logs for that one. You could, but it would be a lot longer. Let's continue. Let's solve for x for this exponential equation because I see an equal sign and I see variables in the exponent. So it's an exponential equation. And notice I can't write 5 as a power of 4. So we're going to need logs. So how do you solve an exponential equation? This is what you should be thinking of when you're faced with an exponential equation. The best way to solve an exponential equation is to bebop to its equivalent log form. So use logs. Logs unlock the exponent. So I'm going to take the log of both sides. I'll do the natural log base e. So doing that, I have this, and you're allowed to do that. That's a property of logs. It's right here. In fact, I wrote down the property. A log property is if you have a equals b, like some number equals some number, like 5 equals 5, then you can turn each side of that equal sign into an argument of a log with the same base. I just made the base a and a here. So if this is true, then that's going to be true as well. So that's what I did from here to here. I just made each side an argument of a log with the same base. Okay, next step. Let's use this log property. This one right here. If you have a log of some argument raised to a power, that's the same thing as you can bring that power out front as a coefficient or factor. So that's a good property. It comes up a lot, like in this case. So first step to solve for x for this exponential equation, take the log of both sides and then use that property I just showed. Make that exponent as a coefficient or factor. And I did that, and I do the same thing over here. Use parentheses because it's this whole thing times that. And if you don't use parentheses, you're going to get a different answer. Okay, so now next step we want to do is use a distributive property. We want to solve for x. It looks tough. we got x's in two places there. Remember, ln of 4 is just a number. It's the power you raise e to get 4. So let's use distributive property next. So 2x times ln of 4, right? 2x times ln of 4, and then minus 7 times ln of 4. And then set that equal to, and again, use a distributive property on the right-hand side. And we get that. Now what we want to do is bring the x terms together because we want to solve for x. So that's what I did here. I brought the x terms together. I subtracted this from both sides, and I added that to both sides. So it gives me this. Now let's factor out the x. That's why we wanted to bring them together. And we have this equals that. And then finally, one more step to go. Divide both sides by that. And there's their answer. Okay, and let's see. Let's try this one. Here's another problem. This is now a log equation. Equation because I see an equal sign, and log equation because I see logs. So this looks interesting. The best way to solve a log equation, first step, make sure it's compact. And this right-hand side is not exactly compact. So let's take advantage of a log property. If you're subtracting two logs, you can write it as a single log and divide the arguments, assuming the bases are the same, which they are, e. So rewriting, I rewrite the left-hand side, and now let's turn that right-hand side into this. Now it's compact. And what property am I going to use next? This property right here. If you have log of some argument equals a log of some argument, if that's true, then that's going to be true as well. So it's kind of like the reverse of the property we did, like this one here. It's kind of like the reverse of that one. Same idea. Okay, so notice that's a good idea to do. So you can just kind of drop the logs, basically. The arguments, set them equal to each other. This looks like a proportion to me. I can write that over 1 if I want. Set the cross products equal to each other, and I've got that. And we want to solve for x. It still looks tough to solve for x, but identify what you're looking at. This is a quadratic equation, a degree 2. And what's the best way to solve a quadratic equation? What do you have to think of right off the bat? You have to think of set quadratic equations equal to 0. That's a good thing to always remember with quadratic equations. 99 times out of 100, you want to set equal to 0. So I did that. And now let's factor. And by the zero factor property, we get these two answers. But before you circle them both with log equations, make sure they're in the domain. You don't have to worry about that with exponential equations because the domain is all real numbers for exponentials. Notice I had to reject x equals -1. It's not in the domain of the original problem. Let's look at the original problem. You can't have a negative argument. And if x is -1, -1 minus 4 is -5. So right off the bat, reject. It works for that one. Does not work for that one. But if it doesn't work for even one of them, then you reject the answer. So that's the final answer. X equals 6. Let me see. How about another log property since I have some time left here? Here's another log property. If you have this, log base a of a to the, we'll say, x power, what is that going to equal? This is a property of logs. Because logs and exponentials are inverses of each other. So this is a cool property. This is like composing two functions, a log and an exponential. And since they're inverse functions, the initial input, which is the exponent, equals the final output. So that property comes up a lot. So notice if the bases are the same, the answer is just going to be the exponent. That's a little bit different from this property because here this base is not x. It's like, call it a if you want. So then you're forced to do it that way. But if they're the same base, then the answer is just x. So now that we know that property, what would this sample problem equal? What is, evaluate that. And the answer is just going to be 7. You can't help but feel like a genius. You can answer it right away because of that log property right here. And then what happens if you compose those functions the other way, an inverse of a log and an exponential? It would look something like this. A to the power of log base a of x. What is that going to equal? So notice it's like I got an exponential and a log in the exponent. So the initial input, which is the argument, equals the final output. So that's a good thing to remember. So what would this equal? 7 to the log base, and I got to use that same base 7. Let's say of 13. Say that's my argument. And the answer of that, 13. Okay, folks, that will conclude that section. Good night, everybody.